Know me, I'm Alex Woolgar. I'm running a research group here at the CBU, and we're interested in how we can use brain imaging to tell us more about how information is represented and transformed in the brain. And as part of that, we set out in a project with Katrina Scrivener, who you heard from earlier at the University of Edinburgh, and in collaboration with Till Grieksvagers at the Western Sydney University, to try to look at ways in which we can improve our analysis pipeline so as to get the most out of our data, given certain constraints, such as having already acquired the data and not being able to go back and redesign the study. And this is basically the question that we are trying to solve. How do we best help multivariate decoding classifiers? Will they do better if we give them just a few stable estimates of activity, or will they do better if they have as many estimates as possible, even if they're noisy? So in other words, if we imagine that what the classifier is doing is learning to separate two classes of points, and then testing that separation on some unknown or some unseen portion of the data, will it do better if it's got few well-estimated points to work with, or will it do better if it has lots and lots of points, even if they're noisy? And it's sort of difficult to intuit ahead of time how those two things are going to trade off. So the actual concept that we're introducing here is very simple. Obviously, it's hard to create more data. You've only got as much data as you can, but we can very easily create fewer, less noisy estimates of our activity just by averaging trials together. So we can average together the responses collected over real trials in order to create super trials, or pseudotrials, as they're sometimes called. And so what I'm going to be presenting today is just some simulations in which we did that, and we tried to look at, does this help us? And if so, how do we optimize that? So the data set we're simulated had 94 stimuli in each condition, the medium effect size, and we used the support vector machine classifier to train and test and decode these two classes. What you can pretend in your head whatever you like them to be. And then on the x-axis here, you've got the number of trials that we averaged together to create each super trial. So where that value is 1, that's akin to no averaging. So this is the basic result that you would have if you didn't do anything at all. And so in this simulated data, there's a mean decoding accuracy of 60-something%, and you can see the distribution over 100 simulated participants here. And then we can look at what happens as you begin to average together more and more trials, creating these super trials, and then training and testing on that. And you can see that at least initially, you have this increase in decoding accuracy, mean decoding accuracy over the group, as you average more things together. So it's in some sense helping the classifier. At some point, you start not gaining so much from more averaging. And if you look at the second, how do I get this back? If you look at the second row of numbers here, these depict the number of super trials it's possible to create. So if you started off with 94 stimuli and you use them all individually, you've got 94 things for the classifier to work with. If you average them in pairs, you've only got 47, and so on and so forth. And you can see that at certain points, like here, where you get down to only having three stimuli for the classifier to train and test on, you sort of don't have so much gain anymore. And obviously things completely fall off a cliff once you've only got 2 points for the classifier to work with, because it means it's trying to train on 1 point and test on 1, which it shouldn't be able to do, and indeed it can't. And then the other thing that we can consider is also there's a number of trials that aren't used. So for example, if you make 15 sets of 6, but you had 94 stimuli, then you had 4 trials that you just couldn't include anywhere. So that also is affecting things. Now, the second thing I'm sure you've already spotted is that as well as changing the mean decoding, this is also affecting the variance. And usually what we care about is something like the ratio of those two things for our statistics. So we can quantify that using just a t-score, which is just the ratio of the mean decoding accuracy relative to the standard deviation across the set. And you can see that initially doing these super trials seems to boost your t-scores relative to doing nothing at all. And this is basically the message of the talk. This is the main take-home point, is that there may be some advantage to averaging things together and allowing an SVM classifier to have slightly better estimates to work with, even though there are a few of them, as long as you don't do too much. But before we go on, we should just check, of course, that we're not creating anything spurious here. So here's another set of simulated data where there's no pattern separation. So decoding is on chance. And indeed, you can average as much as you like, and decoding never goes above chance. You change the variance, but you don't create an effect where there wasn't one, which is obviously important. And so your t-scores sort of hover around 0. Now, at this point, you might be thinking that that's not aligning with my intuition about what should happen here when you give the classifier fewer and fewer things to work with. And we think that part of the reason why it does seem to have some benefit relative to perhaps what other people have done in the past is because we actually aren't creating just one pseudotrial, but we're creating entire sets of these super trials. So I'll take you through how this works. You start by doing what I said already, where you create a set of super trials by averaging together trials in groups of X, so groups of 4 to create 23 super trials, train and test your classifier. But now if you think about how you chose those groups of 4, that was entirely arbitrary and random. And so actually you can go back and do that exact same thing again and create a new set of super trials by averaging together a different combination of 4. And then you can train and test on that. And you can repeat this a whole bunch of times. We did 100 times and then average together those results. So what this allows you to do is sort of hone in on a stable estimate for each person, which then so for each person in your set. So every person's result, every point on this one is the result of 100 creation of these different super trials. And if you don't do this, you get something that is much less useful, where basically you never see any advantage to any creation of super trials because the variance straight away becomes far too big to deal with. Okay, so the next thing we wanted to check was what can we do about the second half of the curve here, where you seem to lose the value of the classifier estimate, the estimates the classifier using being more and more precisely estimated. And we wondered whether resampling could help us here. So the idea with resampling was that so far what I described, you just took each trial once and averaged them together in different combinations. But of course, if you allowed each trial to be used more than once, that would allow you to create more super trials from the same amount of raw data. So you could average 24 things together, but if you used each trial lots of times, you could create many more estimates for the classifier to work with. The cost of that is that, of course, you've now increased the dependence between these estimates because the same data is being used multiple times. So we wondered whether or not this would help to stabilize things. So here's another simulation. This time it's the same 94 stimuli by condition. It's still an SVM classifier. The only difference here is that now we're training on half the data and testing on half, whereas before it was leave one trial out. But the message is basically the same. There's some initial gains, and then after a while, it's not really helping you anymore to have created, to have averaged so many things together. That's if you use one trial at a time. If you allow each trial to be used twice, you can see this sort of stabilization in the second and sort of right-hand side of that inverted U-shaped curve. And if you use it 10 times, it sort of starts to plateau. So there's no real gain here. Like this has never got any better than what you would have done without resampling. But what it does seem to do is stabilize your effect of this parameter. So it sort of means that your choice of how many things you average together became less important. So we can look at the whole space here. On the X, you've got the number of times we sampled each trial from 1 to 10, and on the Y, you have the number of trials in each super trial, and then the T-scores are represented with colours, so you're wanting the warmer colours here. And so if you look in that first column, you can see the effect that I described before. This is what happens if you do nothing. And then with a bit of averaging, things improved. Eventually, too much averaging, things aren't improving anymore. And even with a single resampling, so using each trial twice, you sort of smooth out over that. And so you could look at this whole space and say, well, where do I optimally want to be? Perhaps I want to be somewhere here where a sort of medium amount of trials averaging together in a super trial. Or if I do a bit of resampling, then I can maybe be a bit braver with how many I stick together in each of my super trials to get some kind of optimal ratio of my mean to my standard deviation. And just to reiterate, this is the same analysis done on the data that didn't have an effect in it to start with. And you can see the scale of the T-scores here. Again, we're not creating something where there wasn't one. So it seems like it could be useful to average some things together. Classifiers do seem to perform better under those conditions. So the last thing I just wanted to mention today was where it starts to get a bit more thorny. So how generalizable is all of this, right? If we take one of those plots, you might say, right, I think I want around 12 super trials, then that's going to give me the best possible results, statistical results from my data set. But is that optimal number actually stable? So what about if I was using a different classifier or had different numbers of trials or different effect sizes? And the short answer is no, it's not very stable. So here's the results I've shown you already from an SVM. Here's another classifier, very different classifier, naive Bayes classifier. You see something a bit similar. So you've got this inverted U, though it tapers off much more quickly. And then the LDA classifier, which is another popular choice in decoding and neuroimaging, shows a bit of a different profile, while here it seems to be the case that the more averaging, the better. And if you look across the entire space of these things, you can see that the optimal places are a bit different for the different classifiers. So the SVM's down here, as we talked about, whereas with the naive Bayes, you basically, it seems that the more averaging and the more resampling you use, the more you get this like attractive ratio of your means to your standard deviations. Whereas with LDA, just a lot of re-averaging helps. Resampling isn't making very much difference at all. We also checked what happens with the number of trials. So if you stimulate the same sort of effect size, but with only half as many stimuli, your t-scores are obviously all a bit lower, but actually there's a similar profile. So again, you want to be in this sort of zone with the SVMs, up here somewhere with the naive Bayes, and with the LDA. Again, averaging is good, but resampling doesn't help you. So that sort of seems acceptable. At least ahead of time, you'd be able to know how many trials you're going to have, so you might be able to work some of this out. What's often less clear ahead of time is how big your effect is going to be. And I've already shown you there's an effect when there's a medium effect, and when there's no effect, we don't do anything. So obviously somewhere in between, there are other profiles. Here's a smaller effect size simulation. Maybe the story is sort of similar for SVMs. It's still relatively stable. Like if you were here, you would still be probably doing the optimal thing. With naive Bayes, pretty much most things you do are better than nothing. But now you want to be over here. But if you were over there, you'd still say you probably were winning. But with LDA, and we need to sort of dig into this a bit further, you've got quite a different pattern where now actually doing nothing at all was preferable to pretty much anything else you might do. So these are the circles that we were looking at before. So that was to remind me to point out that in this situation, although the movement in the t-scores is very small, so maybe it doesn't really matter, but you certainly haven't helped yourself anyway. Okay, so these results are not super generalizable. It seems like some averaging helps, but you're going to have to simulate your individual circumstances if you really want to optimize this. And that's all I have to say, just to finish with some take-home messages. So creating these super trials with averaging over super trial sets apparently can increase decoding accuracy, but also changes the variance. A small amount of averaging may be beneficial overall if what you care about is the ratio of those two things. Resampling, it looks like, helps to stabilize the effects, so you're less affected by the other choice you had to make, which is how many trials should you average together to make your super trial. But the inherent benefits of resampling is often marginal. In terms of the parameters we've explored so far, at least for SVMs, there does seem to be this sort of safe zone. So as long as you're creating 12 or more super trials, you're probably helping, you're certainly not hurting yourself. In fact, there's quite a diminishing return after just averaging pairs of things together. So if you wanted to be conservative, that's probably even enough. But to discover the optimal parameters for your purpose, you're going to need to simulate your particular situation. We're going to make some simulation scripts available when Katrina's finished writing up the paper. So you could do this using simulated data, but of course there's going to be the age-old problem of how closely does your simulated data actually simulate your real data. Or optimally, if you had some pilot data that you could leave out from your main analysis, then perhaps you could use that to work out what you might optimally do. And that's all I have to say. Thank you.